Henriksen, and this is my lab report for Lab 4 Circuits and Capacitors. So, this lab was a test of using an online model to predict how resistors and capacitors work in a circuit. And so some important topics that we used for this were the node rule, which states that all current coming into a split in wires is the same amount of current that leaves that split in wires. A loop rule, which says that the overall sum of the voltages is the same, it equals 0 throughout an entire loop, and Ohm's rule, which shows the relationship between volts, current, and resistance for resistors in that kind of sense. So the results we found were that the measured value of our voltage and current matched those predicted by our formulas, and in an RC circuit, the magnitude of current is exponentially time dependent. So some assumptions that we made. So since we're using an online ideal model of the circuit in order to observe the resistors and that kind of stuff, it is assumed that the resistance of the wires and the ammeter are negligible, and that the total voltage generated by the battery is the same as the change in voltage by the capacitors plus the change in voltage by the resistors. So the first setup we had was with 2 batteries on the left, 2 resistors on the far right, and this showed that based off the node rule with the ammeters, that the total reading of current that we got was the same as what we predicted using formulas, which was 0.02 amps. So then we went on to use the loop rule, and it shows that we got 3 volts from the batteries. We lost 0.96 volts from the first resistor. We lost 2.04 volts from the second resistor, and we lost no volts in the wires themselves. So when that's done, 3 minus 0.96 minus 2.04 is 0. And this here is just an overall show the change in voltage throughout those points. So then we went and did a test with an ammeter in parallel with the 100 ohm resistor. And so this one was a little off. We got that the 47 ohm resistor actually had a resistance of 48, and that the 100 ohm resistor had a resistance of 102. This can be chalked up to the fact that the ammeters have fairly low precision, and so that these values might not be as exact. Part 2 was when we moved on to a capacitor, and this was looking at the times it took to charge up a capacitor and discharge a capacitor using both a 10 ohm and 20 ohm bulb. And so for the 10 ohm bulb, it was 10.5 seconds to charge and 12.4 seconds to discharge. And the 20 ohm bulb was 17.3 seconds to charge and 22.3 seconds to discharge. And these times are from when it went, from when the current went to its maximum and then decreased back down to 0. So now here's some data for when we used a 30 ohm light bulb using the same capacitor and same battery setup. And as you can see, as time decreases, the log of the change in voltage decreases. And so from there, we were able to determine the RC for this system. And so in this system, RC is part of the slope. It's -1 over RC is the slope. So with a slope of -0.1668, that, when done correctly, should get you 6 seconds. The expected RC is resistance times capacitance, which is 30 ohms times 0.2 farads, which is 6 seconds. So these values are the same. And so that just goes to show that any and all sources of error here weren't from the models themselves. It was more from human error, either in inputting data incorrectly or not stopping the timing correctly during the experiment. And then we also had 2 what-if questions. What if a real ammeter was used? A real ammeter has some amount of resistance. Unlike what we saw in our computer model, we set the computer model's resistance for an ammeter to 0. And so in this case, we would have to include the ammeters in all of our loop rule equations, and we'd probably get lower values for current. And then what if a real battery was used to charge a real capacitor without a resistor? Well, in the model, we showed that it just charged up immediately, but wires themselves have some small amount of resistance. And so in a real world scenario, it would take a little bit longer to charge up than it was shown in the computer model.